So I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class, this time we have to meet and study your creation. Just pray you be glorified what we do, and that we all understand row reduction and some applications a little bit better together. In your name I pray, Lord Jesus. Amen. All right, so this is the Gauss-Jordan algorithm. And I'll try to illustrate this by examples today. But let's just go through the steps. This is page 13 in my notes. So make sure you have a PDF of my notes to look at. It's really more important than the book in here, for sure. This is the book, really. So first of all, you determine the leftmost non-zero column. That's the pivot column. And the topmost position in that column is the pivot position. If the topmost non-zero column is not in the top row, you do a row swap to put it into the top row. All right. Then step 3 is you add multiples of the pivot row to create zeros below the pivot position. This is called clearing the zeros out below the pivot position. So step 4 is if there are no more non-zero rows below the last pivot row, you go to step 5. Otherwise, there's a non-zero row below the pivot row, and the new pivot column is the next non-zero column to the right of the old pivot column. Then we go back to step 2, and we make sure that we bring that non-zero row up to the next to top row. All right, because our goal is to have non-zero rows in the reduction at the top of the matrix, right? And then step 5. So then you go back, and then you come back to where you go. You do those steps again, that brings you to step 5 then, eventually. The leftmost leading entry in every non-zero row is called a leading entry. You scale the bottommost row to a non-zero row to make the leading entry 1. And then you use row additions to clear out above the 1. So basically, coming up to step 5, we have identified what all the pivot positions are, and we've cleared out all of the entries below the pivot positions. However, at step 5, the pivot positions don't have to be the number 1. They could be 3, 4, 5, whatever. All right. So what you have at step 5 is you've got a matrix where the leading entries could be, they're non-zero, but they don't have to be 1. Then step 5 says you find the lowest one and you rescale it so that the leading entry is 1, and then you use that 1 to remove the non-zero things above the pivot position. All right, so steps 1 through 4 leading to step 5 is called the forward pass. And then past step 5, when we clear out the positions above the pivot positions, is called the backwards pass. Now, I think probably it's best for you just to see me do this for an example. All right, so let's actually do that. All right, so 1, 2, 3, 5, 0, 2, 2, 4, minus 1, minus 3, 3, minus 7. All right, so there's my original matrix. I'll call it M. And I just want to describe to you how we can calculate the row reduction of M. So what's the top, what's the leading, which column has non-zero? Does the first column have non-zero things, for my example? Well, yeah, right? Almost every example we'll ever look at has a first column which is non-zero, but so that makes us work on our first pivot position, which I'm going to circle the pivot position in red here. All right, so my first pivot right here is that, because this is non-zero. Then what I'm going to do is I want to eliminate all of the entries below it and make them 0 with the elementary row operations. So first move here is row 3 plus row 1. So I have 1, 2, 3, 5, 0, 2, 2, 4, 0, minus 1, 6, and minus 2. All right? Okay, so at this point, I have cleared out I've cleared out the non-zero entries below the pivot position. So I'm done with the first pivot. Pivot 1's done. I move on to identify the next pivot position. So, all right, so basically I'm done with row 1. Now I'm looking below row 1. Okay? So below row 1, my next pivot position would be 2. Or you could, in principle, well, anyway, let's just make it 2. There are more than one choice here, but that's the choice that I'm going to make. And then to get rid of this, I'll use fractions. So this is row 3 plus row 2 divided by 2. All right, what's that give me? 1, 2, 3, 5, 0, 2, 2, 4. I haven't done anything. I'll do the modifications here in red. Well, in blue, actually. So that's 0. Minus 1 plus 1 is 0. And 1/2 of 2 is 1. 6 plus 1 is 7. Let's see here. Now, this one here, I have to figure out what is this right here, right? It's going to be 5, my bad. It's going to be minus 2 from row 3, right? Plus 1/2 of what? 4. Also known as?
0.
Oh, hey, that's nice. 0. All right. Okay, guys? So this is our final pivot position, right? So my first pivot, this is the second pivot, and that's the third and final pivot. If you go and look at the algorithm, right, we've done steps 1 through 4. And we've reached the point where if there are no more non-zero rows below the last pivot row, go to step 5. We have now earned the right to go to step 5 in the algorithm because there's nothing to clear out below 7, right? Everything below 7 is already 0 because there's nothing there. All right? So this is the forward pass. Where, we've completed so-called forward pass. I should mention this right here that we have. Well, I guess it depends on which book you read. Some books would even call this a reduced echelon form. So some books would say that this is. I'm going to erase this arithmetic if that's okay. Can I? Well, I'm going to do it anyway. So this right here, some people might call it REF of A. But this is reduced echelon form. REF of A is not unique. That kind of depends on the quirks of your algorithm. Some people would insist that REF of A is such that these leading non-zero entries are rescaled to 1. All right, like I think if you use like a Texas Instruments calculator, you can calculate the ref of a matrix, and you'll find that it has leading coefficients of 1. This is not the reduced row echelon form yet, because notice that the pivot positions, particularly 2 and 7, these guys, the entries above, are non-zero, right? Now, thinking back to the first class, this would still be useful if it corresponds to a system of equations, right? Because if you think of this as a matrix of a system of equations, like this last row would be very easy to solve. It would be something like, if this is the augmented coefficient matrix of some system, then this last row here would be like 7z equals to 0, which gives us z equal to 0. Then you could go to the row above and solve it. We could do back substitution. REF allows us to quickly do back substitution. It's very useful. But let's continue with step 5. So the next step 5 says that you rescale the bottommost entry to 1. So how do I get from 7 to 1? Right, so I do row 3 divided by 7, so the top guys are just the same, 1, 2, 3, 5, 0, 2, 2, 4, 0, 0, 1, 0. All right? And I'll circle this because this is the one we're working on. So now what we want to do is clear out the non-zero entries above the pivot. So how do you do that? How about this? We do row 1 minus 3 row 3, and this one we do row 2 minus 2 row 3. You might be like, ruh-roh, you're doing more than one row operation in this single step. That's dangerous. That's true. It's slightly dangerous. You got to be careful. Some row operations you can do in concert, other ones you can't. Like I can't do a mixture of row swapping and row addition at the same time if the row swap is involved in the addition, because you might do it wrong. So anyway, okay, so getting to the point here. So this does 1, 2, 0, 2, 0, 0 for my first two columns. Nothing changes over here. Nothing changes over here. And this one, I get 1, I get 0, I get 0. Here I get 0 still, and these don't change either because the third row happened to be 0. So at this point, I've cleared out the non-zero entries above the third pivot. All right? This is the beginning. Now begins the backward pass. So we're beginning. Beginning the backwards pass. So next up, we are to this one right here, right? So I can do row 2 divided by 2. That gives me 0, 1, 0, 2. And still got my 0, 0, 1, 0 down here. And my top, I didn't do anything to row 1, so 0, 2, 0, 5. Right? So I rescaled my second pivot row, going back up from the bottom to the top. And then I'll start over again here. So now we can do what? We can do row 1 minus what? 2 row 2. So I'll write the third row doesn't change a bit. The second row doesn't change a bit. But the first row, we clear out the 2. Well, let me put where I'm changing. So this changes to 0. And nothing really changes here. And let's see here. So row 1 minus 2 row 2, what happens there? I get 5, right? Minus 2 times 2, which is 4. 5 minus 4 is 1. We have now completed the backward pass. All right, all of the pivot columns. And then so, going back to last class, the things I was talking about. This is the reduced row echelon form of the matrix. The reduced row echelon form of the matrix because we've completed one way to think of it is we've completed the algorithm, so we're at the end of it. That is by definition the reduced row echelon form. I'm not going to prove it, but in fact, doing the forward pass and the backward pass produces a unique result known as the reduced row echelon form. Just some aspects of it. Notice that this is, like I said last time, E1, E2, E3. So these are my pivot columns, and here's my non-pivot column, right? And the reason for calling those pivot and non-pivot columns hopefully becomes more clear as you understand the terminology pivot position, right? The pivoting is always done within the column. In fact, let's maybe notice something about row reduction is that it goes column by column. There's no mixing of columns. Do you see that? Everything that happens in column 1 stays in column 1. Column 2 stays in column 2, right? So one thing you could say from this immediately, like here's an easy example too. What would be the reduced row echelon form of 1, 0, minus 1, 2, 2, minus 3, 3, 2, 3, 5, 4, minus 7, and then put zeros over here. Oh, here, I'll hand this around. Let me start over here. If you guys could add a day. What's today? 17th, right? So before I forget, because I really don't want to make an announcement, we are having class Monday. You know, like, I will hold class here. You don't have to be here. If you don't want to, you can watch the video later. I don't hold some Teams meeting or anything like that. So if you can't be here for whatever reason because you're, you know, at the inauguration or whatever, that's fine. No problem. You don't even have to, you know, worry about that. Like, I don't take points off for missed days anyway, right? So my point is, I do plan to be here and talk to whoever's here. If it's just me, that's fine. I'll record a video and you guys can watch it later. I don't care. I mean, I do care. I'll be sad if no one comes, but it's true. But, and also, my lectures are generally worse if I don't have students, I found. You know? No one there to catch my mistakes. So, you guys tell me, what's the answer here?
Is it the same thing?
Well, it can't be exactly the same thing because it's a different size matrix, but you said it's the same thing what? Yeah. You're like, it's the same thing with what? With regard to the first what? 4, 0? First 4 columns? I'll say my words eventually here. So, what happens though? What happens to the fifth one?
Still just all zeros.
Exactly, it's just all zeros, yeah. So, let us interpret this calculation in terms of a system of equations, right? Let's think about if we have, so like here's the application of example 1. If I have the system, you know, x plus y plus 3z, x plus 2y rather, plus 2y plus 3z equal to 5. And if I have, you know, 2y plus 2z equal to 4, and if I have minus x minus 3y plus 3z equals to minus 7, right? Then this has my augmented coefficient matrix equals to the m that I gave, right? So we can go through the row operations, and we see that reduced echelon form of AB is, you know, equal to what we just found over here, which was 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 0. Notice that the bar is after the third column now, not the fourth, because this is a different discussion. So then what? What does this mean? This corresponds to the equations what? They're kind of boring. X equals to 1, y equals to 2, z equals to 0. Oh, look at that. So we solved it, okay? So the solution is simply 1, 2, 0. I'd like to point out to you guys that we can do more. This single row reduction can be interpreted in several different ways. All right, let me show you. So that's kind of like the most obvious way to do with M. Like, let's take example 2. What would that tell us? Let's apply example 2 to a system. these aren't really applications in the sense that I usually mean in here, guys, but I guess I think it's a reasonable terminology. We're using the row reduction to interpret another problem. So like the other thing I could think about would be something like x1 plus 2x2 plus 3x3 plus 5x4 equals to 0. And so same numbers, right, guys? Just I'm interpreting the, so now I'm thinking of the totality of M as the coefficient matrix for 3 equations and 4 unknowns here. Same numbers here, guys. So 4, but they have a different meaning now, yeah? Let's see here, minus x1 plus 3x2 plus 3x3 minus 7x4 equals 0. So here's 3 equations and 3 unknowns, right? The augmented coefficient matrix, this has what? So this guy, we have, M with 0 attached is the augmented coefficient matrix for this system, right? And we can calculate, as we just did in example 2, the roof, sorry, I'm an idiot, of the augmented coefficient matrix here is, well, 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 0, with zeros at the end. You might say, well, you don't even really need to write the zeros at the end. You can still figure out everything here without writing those zeros. That's true, but I think we're going to write the zeros so that we understand what we're doing more. Yep.
Isn't it negative 3x2? Around the application, shouldn't it be minus 3x2? Application V2.
Yes. I'll make the correction. And see, if I was talking to myself, that would, thank you. Any questions so far? So my point is we don't have to do any additional calculation to see that the row reduction of this matrix is this. Like we already have it, right? Now let's interpret it. What do these mean? This means that x1 plus x4 is equal to 0. This means that x2 plus 2x4 is equal to 0. This means that x3 is equal to 0. Right? That's the system of equations that corresponds to the reduced row echelon form. The reason that we do row reduction is because it automatically takes the system which we're given, which may be all intertwangled and nasty, and it turns it into something that we should all be able to just read the solution straight off of, because we can always take these reduced equations and rewrite them so we can use the non-pivotal variable, which in this case is x4, as a parameter for the solution set. We can use it as a parameter for the solution set. So here, our solution set is, let's see here, minus x4, minus 2x4, 0, and x4, such that x4 is a real number. And so all I did, guys, was like one more step, right? x1 is what? So now, why didn't I could write the solution set for the previous application. It's very silly. What is it? It's a set which just contains that single point. That's the solution set. There's just one solution. Here, there's an infinity of solutions, right? I mean, geometrically speaking, I think of it this way. If there's one parameter, that means that the solution set's actually a line. If there's two parameters, that means the solution set's like a plane. If there's three parameters, that means the solution set's like a volume. Don't ask me to graph this one, right? We're looking at three equations in four-dimensional space. So every one of these equations represents a three-dimensional subset of R4. And what we're saying is that these three-dimensional subsets of R4 intersect in a line. I can't graph that, but we can do the algebra to figure that out, like we did today already. So I will ask you in the homework to write the solution in the standard form. The standard form for us is that we write we use the non-pivotal variables to write the pivot variables as dependent variables. So like every pivot variable can be recast as a formula in terms of the non-pivot variables. So we can parameterize the solution, if you will, with the non-pivot variables. We can always do this because the reduced echelon form is always going to be such that the resulting equations allow you to write every pivot variable in terms of the non-pivot variables in the solution set. Okay. And there's no ambiguity in writing the solution set that way. If we agree with each other to use the non-pivotal variables as the parameters for our solution set, there's no ambiguity. Is that the only choice of parameters for the solution set? Well, certainly not. Like there is a way you could write this. You could say, well, I'm going to use x1 as my parameter. You could do that. You could use x1 as your parameter, and then that would make this look different, but it would still be the same set. So in the interest of me not going crazy with my grading, let us agree on a standard. We will use the non-pivotal variables to write the solution set when there's infinitely many solutions. That makes it so you can compare answers with your neighbor and make sure you got the same answer. All right. Let's look at another example. So I'm going to shift gears a bit here. There are many more examples of row reductions in the notes, and maybe we'll look at some in a second here. But I think while I'm still writing on the board, everybody got this stuff already? It's exciting. All right, yes. So here's a problem. Suppose f of x is equal to a plus bx plus cx squared, and f prime of 0 is equal to 1, and f prime prime of 0 is equal to 2. Find all such f of x. You guys have a calculus, right? Okay, so I'm not being too weird here. So we've got, now this doesn't look like a system of equations, does it? Right? But it is. We've got two equations, and we're going to have three unknowns here. So let's look at how this looks. So for this kind of problem, I guess my next move would be to calculate f prime. What's f prime? We've got b plus 2cx, right? So hey guys, if you don't mind, I regret my choice of 0. I'm gonna put a 1 in here instead. So sorry about that if you've already worked it out. I'm gonna swap that 1 out, swap that 0 out for a 1 just so the equation's more interesting. Okay, so f prime of 1, and, oh, I guess I need to calculate f prime prime too, huh? (2c). All right, so great. F prime of 1 is b plus 2c, and then f prime prime of 1 is, well, 2c, right? This is given to be equal to 1, and this is given to be equal to 2. So first of all, it's totally dumb to use row reduction here, right? So let me not do that to start with. Let me communicate to you the right way to solve this problem is very simple. We look at the second equation, it gives us what? C equal to 1. And then this one, b is equal to 1 minus 2c, also known as minus 1, right? So therefore, f of x is equal to a minus x plus x squared, where a is a real number. But I'm trying to illustrate row reduction today, so let's look at what this looks like if we did row reduction. So if I look at this, this will give me a chance to introduce some new notation as well. So if I look at this system of equations here, I have 0, 1, 2, 1, and 0, 0, 2, 2. The notation I want to introduce to you guys is when we have a problem like this, and maybe your reader doesn't quite get what you're doing, a simple way to tell them what you're doing is to say, oh, hey, this is my A, this is my B, and this is my C columns. So this says I'm using variable A here, I'm using variable B here, I'm using variable C here, right? This silly example I just made up is to illustrate that we could have a system where the first column happens to be 0, right? So when we apply the row reduction technique, our first pivot is, it's got to be in the second column, right? But this is exceedingly boring in the sense that now clear out below the 1, clear out below your first pivot.
Row 2 divided by 2.
But the row 2 is already 0. So we're already done. It's already cleared out, right? So in fact, as soon as I write down the augmented coefficient matrix, I'm already done with the forward pass. The forward pass is already done here. And the backward pass is just one step. Well, 2 steps. The first step might be row 1 minus 2, just row 1 minus row 2, right? Let me stop using the red here. So I got 0, yowzers. 0, 1, 0, 0, 0, 2. Minus 1, 2, right? And then, oh, I'm sorry. See, look, this actually illustrates another thing, which is the Gauss-Jordan algorithm that I wrote down. It's not written in stone, in the sense that you can still get to the reduced row echelon form without following the algorithm. Like
row 2 minus row 1.
No, I'm modifying row 1. The one that I'm modifying comes first. I think you're asking about this step here, right?
Yeah, yes.
Yeah, so
Yeah, okay.
so it's row 1 that I modified there.
Okay.
So technically speaking, in the algorithm that I've now retracted, I said first rescale the non-zero row to 1, and then subtract copies of it from the so use it to zero out the things above. So this one, what did I do? I zeroed out the thing above before I rescaled by 1, right? And then I rescaled by 1. But the end result is the same. This is the reduced row echelon form of, whatever you want to call this thing. I'm going to call this thing M, and, well, B's kind of I'll call it M, I don't know, I need some other name here. Pac-Man, there we go. So I just decided that the inhomogeneous term here is the Pac-Man. of course, what does this equation reveal to us? What we already knew, right? This is the equation B equals to minus 1, C equals to 1, and A is free. The free variables are the non-pivot variables. They must appear as parameters in our solution set. So the solution set here technically would be like, A minus x plus x squared, such that, A is a real number. That's the set of all polynomials that solve the given question. That's the solution set. Because there's not a unique answer here, right? Now, should you do the row reduction for this problem? I'd say absolutely not, unless some evil professor says, you must use row reduction in your solution. But I probably wouldn't do that because it's annoying, because, come on, this is the way, right? This is the way. All right, let's see if I can find another example for us. All right, so let's look at a couple of examples in the notes here to further illustrate the method. And, guys, you really need to do these for yourself. So, like, the best thing to do is to start trying to do them yourself now. I think you've seen me. Well, listen, whether or not you've seen me do enough, you can try to do it, and you can check yourself with the website that I shared with you guys, right? So that's better than any tutor. The website does not lie. And the website understands in this particular case. So here's a matrix A, 1, 2, minus 3, 2, 4, 0, 7, minus 1, 3, 0, minus 1, 3, 2. So here, this is the more clumsy notation, right? Like, the way I'm writing this in class is what? I would just write this, right? And not even write this over here, because I'm modifying row 2. So first of all, I'm identifying that's the pivot position. I clear out the 2 by subtracting twice row 1 here, right? Then what I did was I took row 1 plus row 3 and put it in row 3, so at this point I've cleared out all the zeros below the first pivot position, right? Then what? Then at this point I want to find my second pivot, but you notice I can't use 0 because it's 0, it can't be a pivot, which forces me to take row 3 and swap it with row 2 and put it up here. All right, then that makes 5 my second pivot, but there's nothing to do in terms of the forward pass because it's already 0 below. And then 6 is my third and final pivot, which brings us to step 5 in the algorithm. At this point, we've finished the forward pass, and that's the REF of A, which again is not unique. So then, for that, I then begin the backwards pass. So I start by rescaling the last row to 1. So I divide by 6. That gives me this. Fractions. But then once you have that, you can easily zero out everything above, right? Because you just add row 3 to row 2, and you add 3 times row 3 to row 1. And that gives us this, and then that, which brings us to, 21/6, 11/6, and 5/6, like as written there. So, yeah, I think the best thing for you is to try to absorb the pattern without trying to write this part, because we can't, if you write everything down for these examples, it will take 2 hours of class. It will accomplish little. You really just need to watch the pattern with me together here for a minute. So anyway, and these notes are posted, right? So you have a copy of them. So at this point, we've cleared out the non-zero entries above the third pivot. So that means we move on to the second pivot. We rescale. Aw, man. Dudes, what happened? Whoa. Oh. the other step must be written in white. Right over here, if you use your imagination in a white font, you can see that I take row 2 and divide by 5. It's right here. Right, which brings us to that. Right, so to get from here, oh, I have it right there. I'm an idiot. I can't read my own writing. Duh. 1/5 row 2. Like, you know. A general point of order. I was smarter when I wrote these notes. Okay? Because it wasn't 8:15. I assure you, I was not writing these notes. I didn't wake up at, you know, a stupid time and say, I'm going to write some notes. You know. Okay, anyway, so 1/5. That gives us the 30th and gives us the 1. At that point, you know, we subtract twice row 2 from row 1. And now all of our pivot columns are the standard basis. We're done. That's the reduced row echelon form. And it automatically reveals that the solution is x equals to 83 over 30, y equals to 11/30ths, and z equals to 5/6 if we think of this problem as corresponding to the system of equations in x, y, z. Does it have to? It does not have to, all right? There are many different interpretations of a given row reduction. We'll talk more about that in future days, but oh, the double scrolling, it got me. Double scrolling. I hate you, double scrolling. I hate you with a perfect hatred. Oh man, I'm like, some of you will have already dropped the class by this time. No one's going to drop. This is an easy class. Do not leave here. Be where you are. Do what you're doing. Get it done. Everybody here can do this. You just need to stick with it. You'll get it. All right. I will eventually get back. Man, goodness gracious. All right, finally. Good night. Here's another one. So let's try to take like a, 5,000 foot view of this. What's happening? First pivot is there. Clear out the things below, get to 1, 0, 0. It's not possible to have a second pivot, so that moves us to the third column for the next pivot, which ends up being this one. And then I clear above by adding, and it brings us to this. So this problem, Why didn't
you do what you did with the last one, to switch row 1 with row 2, give you a pivot for the second column?
Oh, because once the first pivot's done, it's done. Like once you're done with a pivot column, I'll tell you, I'll post a I have a handout from my brother who's also a math professor at Appalachian, and he has a handout for the reduced row for like this whole method, where in his handout he discolors the steps, the part of the matrix which is already done, and sort of just makes the next part not so he like has shaded out the part that's above. So you can kind of think of like shading out, what some people do. Once we're done with pivot 1, you can think about like kind of shading out I don't know. I mean, I don't do this, but you can just kind of ignore that for what follows. You just focus on what's left, which is this, this, I guess. No, that. So you could either use the -3 or the 5 as the pivot. I think it's most natural to use the -3 according to the algorithm, because that's the next non-zero entry that's right below the row, so this is like the top row is the pivot row. It's already the first pivot row. Our second pivot row can't be that one. It has to be a different row. So I don't know if I've answered your question or not, but maybe. So the thing here is, after the dust settles, we see that the first and the third columns are pivot columns for this one. But the middle one is a non-pivot column. Okay, so the non-pivot column doesn't have to be the last column. It can be in the middle, like this. Yep.
Does that basically just happen when all of the lower numbers are 0 for the second column, this is the only time the second one is not pivot column. Like where the second and third row.
Once we've, so when does this happen? When it happens is when we've finished clearing out the zeros below the first pivot column.
Yeah.
And in the next column over, there's also zeros. Yeah. Understanding exactly why this happens and when it happens is something we're going to have to work on understanding over the next few weeks. Yeah.
Is it just because the second and third row, in the second and third row, the first two columns were multiples of the first two columns in the first row?
Ah, yes. Very good. We don't know that yet. So, the gentleman is talking about the column correspondence property, all in good time. You may not understand what you're saying yet, but we will all understand it in time. But that is a forbidden jutsu at this point. So here's a stupid example, a single row. To do the row reduction on this, I just rescale by dividing by 2, and there you go. That's the ribrif of a single row. Yay. A single column. I have to move the 1 to the top spot, and then I can zero it out, and there you go. This is the reduced echelon form of a column vector. Yep. Still, that's how that goes. Yeah, you can have variables. We can do that. Here's another one. So here it's a 3 by 5 matrix, and we do row reduction. Eventually, it turns out for this one, the first 3 columns end up being the pivot columns. So some of you will feel better about that, right? At the moment, you feel a sense of disquiet when the pivot column is one of the first ones, and when the non-pivot column is before. It's not one of the final columns. I don't know. This is always troubling initially, but there it is. That's the forward pass. And so this is the ref. I think where was it? Here. This is REF of the matrix, and then what did I do? Oh, see, I did something different here, right? I'm not following the algorithm. What am I doing? What I did here was to, I think I multiplied the first row by 4. I multiplied the second row by 2. Why did I do that? The reason I did that is just to make them match up so that when I do the backwards pass, I can just zero stuff out without fractions. This is something I sometimes do. All right, so you notice that I've avoided fractions by multiplying the rows so they match up. This is a kind of sneaky way to avoid arithmetic, basically. But anyway, in the final product here, that is the row reduction. All right, so let me move on here. So just to show you, so the next section is on solution sets and so forth. Here's an example. You've got some homework like this. Let me just point you to this example. We'll finish with this for today. But I did an example like that. What if we're looking for a quadratic polynomial ax squared plus bx plus c, right? That fits the points 0, comma, minus 2.7, 2, comma, minus 4.5, and 1, comma, 0.97. So the way to find this quadratic is you plug in these points, all right? Plug in the points into the equation. So I get, p of 0 is c, which is minus 2.7. P of 2 is, 4a plus 2b plus c, which is minus 4.5. And p of 1 is a plus b plus c, which is 0.97. That gives us 3 equations and 3 unknowns, which gives me this, and so here's yet another notation. I've put the ABC to indicate, hey, those are my variables up there, okay? I don't usually put this, I don't like that this is up here. That's not my favorite notation. Anyway, so you do the calculation, and after some work, you get this and this and this. Now, I'm pretty sure that we should use a, some kind of technology to do this. So you guys maybe have had some experience with MATLAB. MATLAB is a great way to actually do numerical examples like this. So I would encourage you to look into that. It's pretty easy to figure out. I'm not going to spend class time on MATLAB, don't worry. But there we go. We get this and that for A and B and C. And so therefore there is a, in this case, unique polynomial. In your homework set, I have given you like a cubic polynomial, but I've only given you like 3 points. So that means that you're not going to find a unique cubic. You're like, I find a family of them. But anyway, we'll talk more about applications Monday. I'm technically a little bit behind my schedule, but we're going to be okay. So if you guys have any questions about, how to do various problems, feel free to email me, and I will suggest something to read.